evening, everyone, to Fiery Tears, Meteor Scatter and the Perseids. We're going to have a look at meteors, what they are, how many there are, and so on. Then we're going to look at the Perseids, what they are, a bit of history as well. And then we're getting into meteor scatter, first communication use, theory of reflection, so how does it all work, and then amateur meteor scatter, procedures, etc. And then a few tools and websites that are useful if you try it. And if you've seen my talk a couple of years ago, there's not too much different. I've ordered it a little bit different, added some stuff for the Perseids, but more or less the same thing. Okay, starting with meteors. There's three main words, definitions that we're interested in. So first is a meteoroid, so a solid object moving in interplanetary space, considerably smaller than an asteroid and larger than an atom or molecule. So little rocks, dust particles, etc. Then we've got meteorites, which are those of the meteoroids that have reached the surface of the Earth without being completely vaporized. So it's a natural object of extraterrestrial origin, so that survived the passage through the atmosphere and then got to the ground. And then finally, what we're interested in, meteors. So originally they were just the light phenomenon resulting from the entry into the Earth's atmosphere of a particle from space, so of a meteorite, and more generally any physical object or phenomenon associated with such an event. So for example, our radio reflections talk of meteors in that respect as well. Okay, sporadic meteors. So there's meteors all the time hitting the Earth. Estimated there's more than 40 tons of matter every day that hit the Earth. All right, so sporadic meteors. Yeah, there's lots of them. So more than 40 tons of matter enter the Earth's atmosphere every day. I've seen estimates up to 200 tons, so not sure, probably nobody is quite sure how much there is. Although I've read in The Guardian the other day that they are going to go onto cathedral roofs and see, because they are undisturbed for a long time, see how many cosmic particles they can find on there. So maybe that will help. Anyway, the size, yeah, from microscopic, very small to several meters in diameter. And the number is inversely proportional to the size, so the bigger the thing, the fewer of them are there. So there's some numbers there. 1 kilo rocks, there's about 100 a day. 0.8 millimeters, we'll see. That's 1 milligram. There's about 100 million a day, so lots of them. And those can be useful for us, as we'll see later. They don't come regular, so there is a variation in the day. There's more in the morning, so you see as the Earth rotates around the Sun and rotates itself. You've got the noon side here, and this is then the morning side. And in the morning, meteorites are swept up by the Earth's rotation, whereas in the evening, that side, meteors need to be faster than Earth to be hitting the ionosphere and cause a reflection. And you see here, this is a station in Germany. You can see for several times a year the number of meteor events per hour that they get. And you see mornings around 6 o'clock. You've got the maximum and the minimum late afternoon, early evening. And that's also noticeable in meteor scatter. When you do that, the mornings are better. So get out of bed and do some QSOs. There's also an annual variation. So we're now in summer, which is ideal. That's the best time. You see there's more than double the amount than in February or March. So that's the sporadic meteors, and then you can see on top of them you've got meteor showers. There's quite a few of them during the year. We'll see them later. Meteor showers were first recorded in Chinese history on the 4th month in the summer in the year of Jin Mao. The sky was so bright that fixed stars become invisible because stars fell like rain. So that's the oldest known record of meteor showers. The first real scientific interest came in the late 18th century, beginning of the 19th century. And then what it really started off was in 1833, a big outbreak of meteors. Denison Olmsted in Yale, he's a professor there. He was woken up by his neighbors, and they could see hundreds of meteors in a very short time. And they all seem to originate in the Leo constellation. And Olmsted, he concluded that the meteors therefore must travel in parallel paths. So the divergence is only a perspective effect. So because they're all traveling in parallel, it looks to an observer like they're all coming from the same point in space. And in this case it was Leo constellation, hence the name Leonids. And then there was another outbreak in 1866 of the same shower, and with that Giovanni Schiaparelli, an Italian astronomer, he compared the orbit of comets with the trail direction of the meteors, and he could show that there is a connection between meteors and comets. Okay, so meteor showers, and especially we want to look at the Perseids because they are coming up.
Yeah, right.
So 1837, the scientists were still gripped by the discovery of the Leonids, and Edward Herrick, he was a bookstore owner in Yale, and he had talked to Olmsted and other astronomers at Yale, and he observed unusual number of meteors on the 9th of August and submitted an article to the American Journal of Science and Arts. And he researches further and finds accounts of the previous years, submitting a second article. But then he must find out that a European, Adolphe Quetelet, he was the founder and director of the Belgian Royal Observatory. He had found that an observer, on average, should see 8 meteors a night. But he also mentioned a higher number for the dates between the 8th and the 15th of August. In the year 1839 then, Herrick and 3 friends determined the meteors in August appear to come from the Perseids constellation. He submitted another article, but John Lockey already in 1834 had determined the radiant, so he complained, showing that he had already done that, so Herrick had to acknowledge the findings. So are there now 3 discoverers of the Perseids? No, there's more. The first record, again, was in Chinese history in the year 36. Then Muschenbrock in 1762 wrote that the shooting stars are observed, especially in August after the high tide has passed, at least in Belgium, Leyden and Utrecht. And there was Dr. Foster's Pocket Encyclopedia of Natural Phenomena from 1827, in which he had copied the manuscript of a monk from earlier, the statement that meteors are frequent on the 10th of August. And then we've got St. Lawrence. He was a deacon of the Roman Church under Pope Sixtus II. He's a martyr, killed in the year 258 by Emperor Valerian. He was roasted to death on a gridiron, and apparently he shouted, "I'm cooked on that side, turn me over and eat." And since then, the Perseids are also known in Christianity as the fiery tears of St. Lawrence.
Remember that phrase? Yeah.
Right, then further on, in 1862, Louis Swift in New York noticed a comet through his telescope, and he thought it was Comet Schmidt, which was discovered, or had been discovered only 2 weeks earlier. But also Horace Tuttle in Maine discovered the same comet 3 days later, so it was named Swift-Tuttle. And Schiaparelli, which we've seen before, he determined the Swift-Tuttle as parent comet for the Perseids. So at this point, I think this will be a good idea to look at this website. Right, so that's the Perseids meteor shower, or a representation of it. You can see the little blue thing there is the Earth orbiting the Sun, and those are the particles also orbiting the Sun. You can turn this a little bit, there you see it, but it's more or less in the right angle. And the Earth is just moving around and hitting it every year around the 12th of August. You see this is moving very quickly there, the date. Okay. Well, that was...
Can I just say something else?
Sure.
Yeah, just see the path that's coming down. That's why the
the radiant's actually in Perseids, which is quite a northern constellation. It's not far from the North Pole equivalent projected in space. So it's coming down like that. And the Orionids, which is sort of later in the year, we're more equatorial, that you'll see that belt of cometary debris is sort of more parallel to the Earth's path, the ecliptic.
Here's one I prepared earlier.
What's that? Oh, there you go. Yeah, so bingo. Yeah, see how it's much more flat. And Orion is near the celestial equator, so it's right between the North and South Pole. But just an interesting fact, the Orionids, it's actually two showers. You get Orionids in it peaking in October, but I think it's, is it the Aquarians or something like that in May? Which where it cuts the Earth's path again, but earlier in the year. So you get two bites of the cherry from that comet.
Yeah. You can see that here, that is crossing the Earth's path twice.
Yeah.
Okay.
The Orion is not much. It's all right. It's not like Perseids.
No. Okay. So that was a little bit of history and how the Perseids were discovered by multiple people. Now we can have a look at communication use and radio observations. So 1925-ish was actually the discovery of the ionized layers in the atmosphere by Appleton and others. And Appleton won the Nobel Prize for that research in 1947. And just a short time later, 1928 to 30, researchers note unusual nighttime echoes in the E layer. The E layer and the D layer, they should mainly only appear during the day because they rely on the sun's radiation to exist. So nighttime echoes are unusual. So 1929, Hantara Nagaoka, he actually thought that meteors swipe away electrons in their paths, causing abrupt change in the refractive index, which isn't right, but that was the first person to suggest the connection with meteors. And then later, 1932, A.M. Skellert published observations during the 1931 Leonid meteor shower, and they show the correlation between visual and radar observations of meteors. And then in World War II, radar in England, for example, was occasionally misled by meteors. So they had meteor scatter which showed up on their radar, and they weren't sure where that was coming from. 1945, research starts at Jodrell Bank with ex-World War II radar equipment. Then 1946, the Jacobinids, those are from the comet Jacobini-Zimmer, and the Earth passed the trail then just 15 days after the comet, so there was lots of meteors there as well, and they did the first velocity measurements and came to a mean velocity of 22.9 kilometers per second. All that so far was radar, so receiving at the same location as they transmitted. And in 1948, Allen then did the first forward scatter research, and he was using FM radio, which in the US at the time was between 42 and 50 megahertz. So that then led to people thinking, well, we might use that for actual communication. And the first people to actually use it were the Canadian military in the early 50s, a system called Janet. There were some more refined experimental systems in the 60s, but it was all not very viable because it was data transmission. And computers were large and expensive, and so they didn't use it much. In the 70s then, with the advent of microprocessors and memory chips, it became more viable, then still mostly in the military. But then in the 80s there was quite a few commercial systems using Meteor scatter. So the Alaskan Air Command system used it as a backup to satellite. Then there's a network called SNOTEL, Snowpack Telemetry Network, which was sending data from monitoring stations like river levels, rainfall, snow, etc., back to the Soil Conservation Service of the US Department for Agriculture. They had 2 base stations and 540 remote data terminals in the western US. Then there were 2 companies who did vehicle tracking or fleet management. They used low-run-C. There wasn't GPS in them days, so they used low-run-C to determine the location, and then used a halo or vertical antenna and a few hundred watts to send the location data back to the base station. And then there is the MCC, Meteor Communications Corporation. They sold their service for commercial satellite backup using Meteor scatter, or Meteor burst communication as it's called in commercial terms. Amateur radio then. In the Perseids, 1946, W2 IXK notes SSB fragments from somewhere. Then the Jacobinids were expected in October 1946, and there were many 50 megahertz 6 meter contacts made then using sideband. Funnily enough, there wasn't much interest after that, so as far as I and others could find. But then finally in October 1953, W4 HHK and W2 UC managed to do the first 2 meter contact, and they won the ARRL Merit Award for that. A few years on, and there was an article in QSD 1957 on VHF meteor scatter propagation, so that explained the theory behind it and also some operating techniques to use. In the 1970s, there weren't many amateurs using it, but there's always some crazy people. In America, they were using mainly single sideband. Again, they used a period, and it's still used like that more or less today. So one station would send, say, the first 5 minutes sending both signs, and then the next 5 minutes the other station would do that, and if they received anything they could send a report, and the other station would confirm that, also send a report until they both got a report and a confirmation. Of course, that relies on quite long reflections to get it done in SSB, so quite a tedious way to make a QSO, but you can do it. Maybe in showers, I guess, they were doing it, not necessarily with sporadic meteors. Europe went a slightly different way, same procedures, but they were using recurs, using high speed, as in 300, 400 characters per minute, and multi-speed tape recorders to record it and play it back slower. Then at some point there was also like that, those were like real tape recorders, and then later I think there was some cassette tape recorders that you could also modify. 1994, DF7KF came out with the DTR, the digital tape recorder, which was a digital device, a little box that you could record audio and play it back slower as well. And the real breakthrough then are the last two, 1997. There was DL3JIN, he had Sound Blaster MS, and the big thing was, I guess, 9A4GL with MS DSP. It was then a DOS program, and later 2000 he came up with a Windows version as well. So that was using the computer to record audio, select it with the mouse, play it back slower, and also to send high-speed Morse, and this was then using really high speeds up to 8,000 characters per minute, so that you could use a very short ping
Burst.
yeah, as well. And then 2001, we all know K1JT. He came out with WSJT version 1, and that brought FSK 441, a new mode used for meteor scatter. Purely digital, about the same speed, also about 8,000 characters it uses. And yeah, FSK 441 is still in use today. I will come back to software and modes a little bit later on. But first we want to find out how it all works. How can we use meteors? So the trail is created when the meteorids, and then therefore meteors, enter the atmosphere. Their kinetic energy is turned into heat that vaporizes its surface atoms, and those atoms then collide with air molecules and are ionized. So that creates a cylindrical trail of free electrons, a bit like here, and they disperse over time, so it creates a paraboloid. So it's, you can see it's wider here at the end, whereas here it's narrower, where it forms the trail. Now we have to look at two different types, and you can't really see that very well here, unfortunately. Maybe on the WebEx it's better. So there's underdense and overdense trail. underdense trail have an electron line density, so the number of electrons per length of that trail of less than about 10 to the 14th electrons per meter, whereas the overdense ones is greater than those numbers. It's not a fixed limit, so you've got transitional trails as well, but that's sort of the division that we do. And the mass of the meteor is less than 1 milligram. So we've heard that there's about 100 million meteors, if you remember, of 1 milligram per day. So those can potentially be used for communication. But as we will see, not all meteors are useful for your specific contact. In the underdense case, the radio wave penetrates the trail and excites the electrons, and they re-radiate the energy. Whereas in the overdense case, the radio wave can't penetrate the trail, and the reflection is more of a metallic cylinder. And because there's winds up there as well in the E layer, wind shear causes parts of the trail to move, and then you can get interference by reflection of different parts of the trail, causing fading. So to explain those pictures a little bit, this is, I think, about a second, and you see a sharp peak when the trail is created, and then an exponential fall in the signal strength until it's back to the background level. And this is about 10 seconds, I think. So this is just an example number, and you see it starts slowly, rises, and then falls slowly again, and you can see also that fading caused by the interference pattern. We will focus on underdense because there's many more of those, and we want to use those for our communication. The overdense, of course, are nice long reflections, sometimes very strong as well, but there's not so many of them, so unless in a shower, they're not so useful. Okay, so I said that not all meteors can be used for your reflection. So reflection is specular, like from a mirror, so same angle that your ray goes to the trail, it is reflected out of it. Trail is perpendicular to the plane of propagation, so the plane of from transmitter to the trail to receiver. You can see, you can imagine a plane through that. I've got a diagram on the next page that shows that a little bit better. And that's basically equivalent to that the transceiver and receiver are at the foci of a prolate ellipsoid with the trail tangent to it. But of course, in addition to that, you also need your trail in the right height, so in the E layer, between 80 and 105 kilometers. So that's another restriction of the number of meteors you can use. There's a nice formula that we can use. That's the received power. We don't need to understand it fully, but we can see, so this is the received power at a specific time, with the time equals 0 when the trail is created, so when the meteor is just passed. These are just constants really, apart from lambda. So transmitter gain, transmitter power, receiver antenna gain, pi is the echoing area of an electron, and we see we've got lambda to the power of 3. So
frequency, less power.
yeah, exactly. The higher the frequency, the less power. I was just getting confused with it being on top, but it's lambda, not f.
Yeah,
Yeah, so you can see if you compare, for example, 50 megahertz and 144 megahertz, it's about 3 times. So got about 9 times more signal on 6 meters than on 2 meters. And you can see here also lambda goes into the length of the reflection. So we've got e to the minus t here, and we've got lambda to the square in that term as well. We can also see sin square phi, where phi is this angle here. So that means that if that is greater, we also get greater signals. So that's longer distances. So that's good. Okay. So we see the higher the frequency, the less signal, which we can compensate for a little bit, because of course on higher bands we can have more antenna gain, and also the reflection is shorter the higher the wavelength, the higher the frequency. Okay. Then there are hotspots. So if you look at, if I go back, at this diagram here, you see in this example already, you're not beaming as the transmitter, you're not beaming on the great circle path to the receiver, you're beaming a little bit off it. And that's a reason. The reason is there's a slow probability for near horizontal trails, so those are flat on top of your ellipsoid, because meteors going that way wouldn't either wouldn't go into the E layer, or they would jump up, be forced off it at the top. Yeah, scoot off. So those are rare, and also near vertical trails. If it's vertical, it doesn't work, because vertical would be on the ground, not 85 kilometers high, so that doesn't work. So in the real world, you get hotspots about 10 degrees off the great circle path. Depends a bit on the distance, but even on longer path, you still get those few degrees off the path. And it depends also on the time of day and path orientation. It would be equal on both sides if there was a equal distribution of radians, but for example, in the morning, got more, or in depending on your time of year, also the radiant would change, because in the morning you would see them more southerly, which would cause the hotspot to be on the north. So if you imagine you can see the meteor coming from the south, which would mean it passes over you and then goes down in the north, and that's where you have the reflection point. So then, depending on the time of day and path of orientation, whether it's east-west or north-south, you get a specific hotspot, and you don't have to calculate all that. Fortunately, the software will give you the direction of the hotspot. Okay, don't think we need to go that much into the theory, because you just work what you hear, but it helps if you look into the right direction, of course. So, meteor scatter. Firstly, let's have a look at what bands and modes can we use. Well, you can use it on upper HF on 15 and 10. The band's closed at night. You can still do QSOs. Reflections aren't that short. Low frequency, so long reflections, loud signals.
Do people do that much?
I don't know. Probably not normally for normal contacts, but
If you get them through ground contact anyway,
yeah, you would normally just change band to lower band. But yeah, if you're in a contest looking for that multiplier and short QSO, you just give it 5.9 and a number. That can be enough in a reflection. Definitely works. So yeah, on 10.15, a very good candidate is the ARRL 10 meter contest in October, if that falls on the Geminids. The Geminids? Or Orionids?
Wouldn't IOTA be?
No, it's December, isn't it? ARRL 10 meter. It's after the CUO line.
Right, so that's Geminids.
Yeah, that would be Geminids. So if it falls on that maximum, then there's lots of contacts using those.
But CQ Worldwide is up to that. But the Orion isn't a really big shower, to be honest.
No.
Say IOTA, right? I mean, it's not quite in the middle of Perseids. Would that not be an option?
No,
I
that's
think
too
that
early.
should probably show a very sharp peak with the Perseids.
No, actually, the Perseids are not that sharp.
You sure?
I think so. There's multiple as well. Multiple peaks.
Right,
I am.
I'll let you know.
That's what I found, anyway. Okay, upper HF. Yeah, so it's not a meteor scatter band as such, but you can use it. 6 meters, of course, you can use CW sideband as well, and people have been for a long time. I've worked, for example, for U1 ITU when there was no conditions at all. I think Don G3BJ was there, and it was summer, so you'd expect some sporadic E, but no. So he was still securing, and there was the odd burst. You could hear part of the CQ, but then one time after a couple of hours listening, he came up, I gave my call, he gave me a report, I gave him the report, and that was the QSO done. Nothing heard afterwards. So yeah, it's always useful, but it can take time till you get one of those overdense reflections and do a QSO with it. But the the main modes for Meteor scatter is MSK144, that's definitely the main mode. There's a few older ones like JT6M, that's often used in the activity contests in the week because they require a 4-digit locator, and that you can basically send free text, whereas with MSK you're limited to the format that it provides. So for that they use JT6M. 4 meters, again MSK, I guess in a way all the others apply as well, but the main mode there is MSK144. 2 meters, still the old FSK 441, even though old Joe Taylor has removed it from his software, unfortunately. There is MSK 144, which is a bit deaf on 2 meters because it needs a specific length of reflection before it decodes, because it's either all or nothing. And it's got forward error correction, so you need to get all the bits, or a certain part of them anyway, reflected before you get a decode, whereas with FSK you can get partial decodes as well because there's no error correction or...
Just a question, the 441, that's a bandwidth, isn't it? Is that
No, that's the...
Because it allows a very rapid burst, which presumably is a high bandwidth.
Yeah, but the bandwidth is 2 kilohertz for both of them.
Oh, right. What byte rates?
It's to do with the coding scheme, but I haven't looked at those details, to be completely honest. So that one is still in use. MSK is still in use, which works, but yeah. But I've had, it was also during a shower, don't know which one, not too long ago anyway. I was calling CQ and I heard pings, short reflections every period from someone, but none of them decoded, so nothing I could do other than continue calling. And then somebody connected to me on the chat and said, I'm calling you, and okay, let's try FSK, switch to FSK, and QSO was done in 5 minutes. So yeah, it's convenient, MSK, but it's a bit deaf. On 6, because the reflections are longer anyway, it doesn't matter, but on 2, it just doesn't work. And on 70 centimeters, and 70 centimeters is really not a Meteor scatter band. It only works in showers really, and yeah, very short reflections, of course. 23 centimeters has been tried.
I'm saying potentially this new 8 meter band could be open for it, could it as well?
Yeah, that will work. Yeah, 23 SAMs has been tried and reflections have been heard, but I'm not aware of any QSO that was completed. And that was with big dishes. Okay, what hardware do you need? Of course, all-mode transceiver with the data interface as usual. Power, the more the better. 50 watts, make sure your transceiver can do the 50% duty cycle. 6 meter and 4 meter, maybe a dipole minimum. Depends on the other station as usual, of course, and in a shower it works better. Outside a shower with 50 watts and dipole it might take a few tries to get a QSO completed. 2 meters, probably a 5 Yagi, the longer the better. Smallest station I've worked, as far as I know, was 25 watts and a 5 element Yagi from Italy. 70 centimeters, you need a long Yagi preamplifier, and it only works in showers. They usually do 2-hour scats. And yeah, a good quiet location helps. Increasing ERP as well, either by antenna or power or both. So, question. Who has got the hardware to do Meteor scatter?
Potentially, yes. Potentially, yeah.
Okay. Good. Then back again to software, we sort of mentioned it. WSJT-X, which is the current by K1JT, version 261, and that has MSK144 as the Meteor scatter modes. Then the program I use mostly for MS is MSHV by LZ2HV. Version is actually 272, came out yesterday, and that's got all the Meteor scatter modes. It's got FSK 441, there's another FSK 335, I think, that's similar, but that's rarely used. MSK 144, JTMS, JT6M, and so on. And then, if you can still download it, I couldn't find the download site now anymore, so maybe it's been removed. By K1JT, current latest existing version is version 10, and that does FSK 441, JTMS, JT6M, those modes, but it doesn't do MSK because that wasn't invented by the time. So my recommendation is go with MSHV, because that's got all you need. It does FT8 as well if you are so inclined, or JT65, those weak signal modes. Okay, then calling frequencies. There is a few. So on 6 meters is 5280, even though the band plan says 5360, but that's not used. Then 4 meters 70174, and there you use MSK 144 as mentioned, and there is a period that you can set. So you use 15 seconds periods on those bands. You transmit 15 seconds and receive 15 seconds. And on the higher bands, you use 30-second periods, and calling frequencies are 144.360 for MSK and 144.370 for FSK. More traffic, even though the depth mode is on MSK. It's for random QSOs, it's got the advantage that you really get the whole message, if you get anything. But there's still people on 370 from time to time as well. And a lot of QSOs are also going on with SCADs, so you do a SCAD. But for random, you call CQ, and you should, especially in showers, call with a QSY frequency. So for example, if you're on 2 meters, 360, you call CQ353, then you'll call. And what happens is the other station will reply on 144.353, and then the QSO will continue on that frequency. When you hear them, you reply on 353 until the QSO is complete. So it's not like split on HF where you use two frequencies. Once the contact is established, you stay on the frequency of the calling frequency, pretty much like on SSB as well. Call on 300 and say, let's continue on 320 or whatever. And that's where you continue your QSO. So I mentioned SCEDs, and there's multiple ways. You can go onto the ON4KST chat. You can email, get the address of QRZ and send people an email, or if you know the person, send them a WhatsApp or whatever communication medium you prefer. Then you set your frequency, your mode, and well, the period length is usually clear, but you have to say who's using the first period and who's using the second period as well, so, or odd and even. And then a QSO. The procedure and the QSO format is very much, oh, that's a weird color on the screen. It's yellow. Is like FT8. So here's the period length again. And the UK usually is using the second period, so to make sure that UK stations don't interfere with each other, they usually all call second and then the others reply. So it's really IO and JO squares should call second, and what's around it should call first. But of course there is always, if you're inside of that, you have to make a compromise. And that's also why you would want to go off the calling frequency, because it will cause QRM. Because it's not like FT8 where you've got a 50 Hertz wide signal, you've got a 2 kilohertz wide signal, so you're basically using the frequency, and others wouldn't be able to hear anything. So I don't know if you can't really see that, it's a bit small. I thought it would be bigger, but you see here I'm calling CQ, then GG IV3 GTH is giving me a report. I hear that, and this is a quick QSO, send a R report like an FD8, and I get a RR73 or triple R back, and send my 73 as a courtesy. So once one station has received, or both stations have received a report and the confirmation that the other station has received their report, the QSO is complete. So you don't need to send 73, but it's a courtesy, and also helps for the other station to know that the contact is complete. And you see also the graph is slightly different. So you have the frequency vertical here on the x-axis, and you've got time, on the y-axis, and you've got time on the x-axis. You see 0 to 30 here at the top. Here is a little reflection, you can see. On FSK, it's slightly different because you can receive partial calls. So you start with sending each other's call sign. So if I want to call, as we'll see in the next slide, S51TA, I say S51TA G0SYP, S51TA G0SYP, and so on. And when you can identify that your QSO partner has called you, so you get partials of the calls, then you can start sending a report. And as soon as you have got both calls and the report, then you can either send TX3, so the R report, or if you've got the R report, then you can send RRRs. Rogers. And the QSO is complete when the other station or you receive a string of 3 or more Rs. And the reporting is 2 digits. First digit 2 to 5 is the length of the burst, and the second digit 6 to 9 is the signal strength of the burst. So if you give somebody a 5 and 9, that means they were longer than 5 seconds with at least S5. So that would be quite rare. Okay, here is, and again, it's unfortunately a little bit too small. Apologies. So I received the first part. This is a QSO with S51AT, Boris. So here's the call. This is MSHV. You see his locator as well. You can see in the middle there's a few settings. So you've got the DF tolerance, and you've got that on WSJTX as well. So that's the tolerance, how far off the nominal 1500 Hertz center frequency you decode. So if somebody is 100 Hertz off, and you've got the tolerance set to 200, it decodes fine, but if they're 250 Hertz off and you've got it to 200, then it won't decode. And that's another advantage of MSHV. Here you can only set it to 200, in MSHV you can set the tolerance up to 400 Hertz. Okay, so here I get partials, I get my call. I think you can see an AT there somewhere, but inconclusive. But I have received confirmation that I'm being called, so I can start sending a report. This is a scan. I can start sending a report. So I would send S51AT G0SYP 2626 repeatedly over and over. And let's see if this works. This was the weak one. I've got stronger ones later. So this is the second part. As you can see here, that's another thing that's specific to FSK. You can click on the reception where you see it, and you can click somewhere else for it to try again, just to decode something. Sometimes that helps. And you can also change parameters like your DF toll if you have it narrow and the station is further away. You can set it to a higher value and then click again on the waterfall and decode again, and then it might decode. So I tried here to get more information out of it, but my call was all I got. But here in the second reflection I got can't see if, no, that's not my call, but I got his call, S5180 2626. So now I've got my call, his call, and the report. So I can send a confirmation, so I can switch to sending S5180 G0 SYP R26 R26. And when Boris receives my report and all the other info, he will send RRRs. So I've got that here in my TX4, 4Rs, 4Rs, and G0 SYP. For FSK, the synchronized signal is basically the space. So that's why there's some spaces in there as well. Otherwise you could put 8 R's together, but it's better to have a space in there to have it find the synchronization. Okay, and here finally I've got the RRR, maybe even twice. Can't see if that's the same. No, it's, yeah, there's two bursts in one period, both are decoded RRR80, so he's just doing the short form, not sending the full call sign as the suffix. And I can start sending 73 to complete the QSO. Let's see if you can hear those better. That's all required. Okay. Any questions so far on the procedure? Is that clear? Okay. It's a bit complex, but once you've done it once, it's straightforward. So then, to round it off, some tools and websites. So to find out how many meteors there are this specific day, you've got SGO, that's Finnish Observatory in cooperation with the University of Leicester. So they've got these two graphs. So this is just the echo count against the long-term mean. Probably a bit of an untypical day. Normally it's really more like this, with the odd ups and downs, but not like this. This could have been, because it's quite northern in Finland, could have been affected by some disturbance in the atmosphere. Okay, so it gives you this, and it also gives you the number up here. It should be for the same day. It gives you the number of meteors and the height as well, the height distribution and the direction. So that's finding out what's happening at the moment, or at least in the last half hour. Then there's a tool called Virgo on DL1DBC. You can either run it on the website directly as a Java applet, or you can download it as a Java file and run it as an executable. You enter your locator here, and it shows you the currently active showers. So you can see here the Perseids are there. See the date, 25th of July. So the Perseids, you can see when they rise and set, because the Perseids are northern, as Evan mentioned. They are above the horizon 24 hours from here. So no break. Whereas other showers from southerly radiance only are there for a few hours in the night. Look at the Alpha Capricornis down there. And it shows you the class. So the lower the number, the better the hourly rate. So that's a number, that HR. Zenithal hourly rate is basically what person in a perfect location, if the radiant was straight up, what they would see, the number of meteors they would see per hour. Of course, the higher the number, the higher also for radio meteors. There's no real good relation with the number there. So that's a tool. Then there is MCG MS by DL5 MCG, and for some reason I only found this about half a year ago or so, which is a good tool. You enter the other your locator, of course, the other station's locator, and the date, and then it calculates a efficiency between 0 and 100% per hour. So for this locator, I don't know what it is, I think it's KP15 or something in Finland, and it's the Perseids as well. Around noon, 12 UTC would be 100% efficiency, so that would be the best time to try a contact into that direction. It also shows you north, south, east, west, and northeast, southwest, southeast, northwest directions. And you can then click on efficiency graph and show best direction, and that will show you the graph on the right. So red is good, black is hopeless, or at least you can't use any shower meteors for that. If you do a contact, then it's either a different shower or sporadic meteors you're using. So again, that's a good tool to plan, especially for SCADs. You can set a date other than today, so you can plan on this and that date for that shower. We might try at noon, in this case. I don't know exactly what the number means, or qualitatively. Of course, the higher the number, the better, but I don't know how many meteors you would get, and the signal strength that you would get for that.
Point. I mean, I don't do meteor scale, but I sometimes listen to just the meteor count. If you tune into the Grave radar in France, which is to our southeast.
Yeah.
I'm just thinking like the southeast, northeast there. Because if you want to get the highest number of meteors to just hear them zinging through your headphones, you probably want to use something like that. So that would look like midnight, early morning at the moment for the Perseids.
Yeah.
Or the 12th. Because I'll put something on the website about this. But yeah, if you just want to listen to the meteors and hear what they sound like, it's a VHF. It's basically a constant carrier satellite detection radar. So when you get the geometry right, you hear the zing of the meteors through that. And of course, there are certain times where that's there. And if you just look, you just go back to the Virgo one. so you've got the two choices for that direction, that compass on the right, and looking at where the Perseus radiant is at the moment.
Yeah.
Given that.
You see that west is there and east is there, so this is for an observer who wants to like hold his tablet up at the sky and then find where to look for the meteors. That's why you can also use it for. That's why. But you can switch it.
You select meteor trails as well. You notice that should be 90 degrees off.
Yes.
So you probably, this is a real time thing. So, but I'd imagine, say midnight now, this is where you get the meteor trails, things sort of northwest, northwest southeast.
Yeah.
And that's where you listen to Grav.
Yeah. We can try in a minute if we can get that. Yeah, so that's useful. MCGMS, very useful. And then there's a few other sites. OH5IY. He has got a similar software, but it's only DOS. So you need a DOS emulator, and I've had issues with that, so I've given up on it. But the website is still very useful because there's loads of information about meteor scatter on there. If you look for the help file for MS Soft, there's lots of information also about the history, what I've talked about, and the theory, some of his experience. For example, he has got a graph there on the success rate that he had with meteor scatter on 2 meters versus distance, and there was a clear maximum around 1400 kilometer, and then after that it was down quite considerably, so the longer the distance, the more difficult it is. I didn't even say it's a few hundred kilometers to 2,200 kilometers in exceptional cases, a little bit more than that. But that could be also linking into Tropo or something. So I know some people have worked the Canaries using Tropo over the sea in front of Africa, and then meteor scatter for the rest. So well worth a look there, even though the software you can only run on DOS. KST, ON4 KST, the chat that I've mentioned, there's 2 chats, or there's more than 2, but the ones interesting for us would be the 50 and 70 megahertz one, which is also useful if you're into 6 meter DX. Get some information there, lots of friendly, helpful people. And then there's the 144, 432 megahertz chart if you want to do 2 meters. And then there's others, there's microwaves, low band, EME, etc. Then Make More Miles on VHF is a website, and one of their entries is monthly meteor scatter activities, so they tell you for each month which showers are active, when the maximum is. Depending on the bigger ones, they tell you what direction to look for, etc. There's the expedition announcement, so if anybody's going to a rare square, that could be announced there. That's the website. DK5YA's VHFDX website is old. It's not maintained very well, but there's a few good links on there still. So that's useful. And then if you want to know when the showers are, there is meteor shower calendars. So there's the International Meteor Organization, IMO.net. They've got a very good calendar as a PDF with some background notes as well. And then there's AMS Meteors, or the American Meteor Society. But the next one that we're all interested in is the Perseids. It's already active, but there's only a few meteors at the moment. The peak this year is on the 13th of August, supposedly between 7 a.m. and 2 p.m. UTC, and the hourly rate is 100 for that shower, so you can see it's second best really. The best is the Geminis, definitely. In December, that's a very good shower. Quadrantids in January, short but also quite good. And then there's some others. So with that, get on the air. 13th of August is a Sunday, so that's useful. It's a weekend. The good rate starts a few days earlier, so it's not like in the maximum, but you can definitely notice an increase, and also there's more activity, which also helps. Get on, listen to the calling frequencies, use one of the tools to get the best direction. If you're calling somebody, don't be fooled necessarily by over-dense reflections. Wait till you hear them maybe a couple of times, because that might just be a one-off big reflection and the next one is an hour later, and that's a bit long for a random QSO. Then make sure you reply on the correct frequency, but the software does that for you. If you double click on it, it will automatically QSY if you have the rig control configured. And the most important thing in Meteor Scatter is patience, because sometimes you just have to wait and then it happens, because meteors appear a bit like buses in clusters, and some other useful things. The other person's reflections are always better. That happened to me this morning. I heard CT7 in QSO with DL and heard 5-6 pings during their QSOs. So I had all the information for them, could have completed earlier than them. And then I asked the CT7, should we try? So we tried, and after half an hour I had 2 partial decodes, and that was all. So a bit of luck is helpful as well. Okay. Thank you.
Okay, thanks very much indeed, Carson.
Absolutely, well done, Carson.
Appreciation, please.
Hey, Carson, all I can say is you were very brave to tackle that subject.
Yeah.
Especially with you sat there.
No.